Good afternoon, everyone. My name is Aaron Graham, and I'm the founder of Cognitive Infrastructure Labs based in Princeton, West Virginia. The concept I'm presenting today is called the Complete Cycle Mine-Water Thermal System. The operating philosophy is borrowed from the Native American stewardship. Use every part of what the land provides: the water, the heat, the elevation, the void space, even the elements that are around the mine site that have been left there. Let me start with the problem we are actually solving for right now. Data centers are growing faster than communities can absorb them. And we know this because Virginia, the largest data center market in the world, commissioned a full state audit. The audit found is instructive: land disputes, transmission corridor conflicts, diesel generator emissions that were generally difficult to model at the neighborhood scale. Tax-sensitive debates were the public questions whether the benefits matched the burdens. Water consumption that in 2023 reached approximately 66 billion liters directly consumed by U.S. data centers, and nearly 800 billion liters indirectly through the electricity those centers drew from the grid. This friction alone is one of the reasons why abandoned mines can be used, because they have the water, they have the elevation changes, and they have stable underground temperatures, roughly 50 to 60 degrees Fahrenheit, year round. Naturally, without mechanical assistance, they have void space that can absorb the thermal loads, and in many cases, they carry existing permits, roads, and power access already in place. The question that I keep returning to is simply, what if instead of fighting over where to put the next data center, we use what the land already has? These abandoned mines are not magic. They introduce real engineering burdens: flooding, methane, geotechnical risks, ventilation, safety. To get all that, but the resources stack they contain is documented, not speculative, and it is what makes it worth a disciplined look. Below, I show you the site data. Let me explain the circular logic. This makes the cooling system: mine water is cold, stable, and flowing, enters a closed loop heat exchange to cool server loads. The water absorbs waste heat from the IT equipment and returns the heat underground, which several people have already talked about. And the thermal mass of the mine slowly dissipates. The water path drives micro hydro turbines, recovering hydroelectric energy that partially offsets pump consumption. An AI supervisory control layer predicts thermal loads, manages water chemistry, and optimizes the balance between pumping cost and generation revenue. Every element on the land is provided, is used, nothing is wasted. I began researching the concept. I focused on a specific site in West Virginia, the Rock Creek Development Park, formerly the Hobit 21 mountaintop removal operation in Boone and Lincoln County. What I found was not what I expected. It wasn't a hazardous wasteland. It is 12,000 acres of reclaimed site with an active 340-acre surface reservoir containing somewhere between 1 and 2 billion gallons of water. Documented flow capacity of around 2,000 gallons per minute. The site has a valuation differential of 25 to 200 feet, enough to drive micro hydro turbines, and estimated 60 to 50 kilometers per installation. Depending on the head and flow, at roughly 65% turbine efficiency. Active NPDES permits are already in place, which means the water is already being regulated. The Boone County Public Service District has secured $4 million for local water infrastructure tied to this area. The site qualifies for West Virginia AMLR program funding, the Federal Abandoned Mine Land Economic Revitalization Program. Let's be clear about what this means. The water resource at this one site is large enough to close loop liquid cooling systems using mine water at the heat sink would have thermal capacity measured in megawatts, not kilowatts. The elevation head provides free hydraulic energy, water flowing downward through turbines and returning upward near neutral energy loop, absorbing heat peaks during high load periods and releasing them during low periods. On the carbon side, West Virginia's grid carries CO2 intensity of 0.893 kilograms per kilowatt hour. From EPA and eGrid database in 2023, that is one of the highest intensities in the nation, which means if you can generate electricity on site or substantially reduce grid draw, the emissions benefit in West Virginia is larger than it would be almost anywhere else in the country. Coal mine methane is part of the picture, but we want to be careful with that because we don't want to use it, but we have to watch it. So we have to plan with our systems. Go here to the next slide. This is part of a talk where I wanted to direct about something. West Virginia has 130,000 acres of abandoned mine land. It is not one problem, it's 130,000 acres of problems with different water tables, different methane profiles. A rigid blueprint fails in this environment. What I'm proposing is a flexible template, a stage gate engineering process that can be applied to candidate site, adapted to what the specific site actually contains. The template has 4 interlocking layers. First, a thermal layer, mined water at stable 50 to 60 degree Fahrenheit circulates through heat exchangers to cool server loads, then carries waste heat back underground or into surface recapture for winter heating. The cooling energy index drops from 1 at 55 degrees to roughly 0.38 at surface summer temperatures at 75 degrees, meaning the mine baseline delivers approximately a 62% reduction in relative cooling energy demand compared to a hot summer day. This is one of the real advantages of abandoned mines. But it depends on the cooling system design, not just the temperature. Second, a hydraulic layer, water flowing downward through elevation, differentials, drive, micro hydro generation. That same water treated for chemistry returns upward through the pumps, partially offset by the generation. A well-designed system approaches hydraulic energy neutrality for this closed-loop language. Third, an AI supervisory control layer. This is not an AI buzzword, but let me go back a couple steps. There we go. Predicting thermal loads and pre-positioning cooling capacity, managing pH conductivity, and scaling inhibitors to protect heat exchanges, optimizing the moment-to-moment trade-off between pumping cost, micro hydro generation, and battery storage, and respecting hard operational constraints on flow rate, water temperature, and methane concentration at all times. Fourth, the governance layer is the layer that determines what the template is development model or just another extraction operation. It includes a community benefit agreement with measurable local hiring targets, local procurement. Now, with the risk, let me go over to that.
Sorry, Aaron, we've got some slightly different slides in person than we do have online, so we're just trying to keep
Yeah,
up as best we
sorry
can.
about that. The engineering risks directly, the risk register shows 8 primary categories. Geotechnical and mine water flooding are both medium likelihood. Risk scores of 9, ventilation and methane accumulation scores 8. Methane explosion is a very low likelihood. So we have to watch for that, but very severe. Fire suppression regulatory jurisdictions, financing overruns, and permitting delays round out the register. None of these risks are disqualifying. All of them are manageable with appropriate engineering discipline. Full geotech characterization before commitment, redundant sump pumping, continuous methane monitoring with automatic shutdown at MSHA threshold, ATEX grade electrical equipment, zoned ventilation that separates mine atmosphere from the IT environment of the data center, and early regulatory consultant before any construction decisions are made. On the cost side, the JL's 2025 benchmarks puts global data center construction at approximately $10.7 million per megawatt. Underground conversion adds mine rehabilitation and life safety costs at roughly $4.5 million. Along with the range is deliberately wide because the subsurface conditions are variable. The AMLR program, co-investment from the county infrastructure partners like the Boone County PSD, and reduced land and noise mitigation costs partially offset that premium. The full economic case requires a site-specific feasibility study at the end of stage 1. The pilot roadmap right there is 3 stages. Stage 1, 0 to 18 months site characterization, full geotech and hydrology survey, mine water chemistry baseline, thermal profiling, portal safety assessment. Stage 2, 18 to 36 months integrated pilot, thermal loop and pump integration, active chemistry monitoring, heat exchanger commissioning, micro hydro turbine installation, the AI supervisory control prototype deployed. Stage 3, 36 to 60 months, scale decision measurable PUE and WUE results, methane pathway determination, full economic validation against the feasibility model. The
Thanks, Aaron.
template,
Can you conclude with this last slide? Just got 1
yes.
minute left. Thank you.
I wanted to close with the same discipline I opened with. The resource stacks at Rock Creek and at hundreds of abandoned mines across West Virginia are real, documented, permitted, and circular logic is coherent. Water cool servers, heat warms buildings, gravity drives turbines. But the proof requires a pilot PUE and WUE methane pathway. Geotechnically, safety and economics must be measured. The narrative must be honest. This is not magic mining cooling. This is disciplined circular resource design that earns belief through evidence. Thank you.